Start recording. Okay, so first, some logistics. Team should be assigned. You can pick up your cars tomorrow and day after in the office hours. And homework one should be released. Homework one doesn't actually need the car. You just need to, you can use the VM or the workstations in the lab, but it's relatively easy. It should take you not too long. No hardware component, just like it's trying to get you used to the software. That's it. Okay, so we talked about robotic system design. Today we're going to get into the details of filtering and localization. Right. So the important thing we covered last time was the Bayes formula, right? Or the Bayes rule. The Bayes rule tells you if you have P of X given Y, you can write it in terms of P of Y given X and P of X. Right. And we're going to try and use that to construct our Bayesian filter. Right. And so specifically, we're thinking about the problem of state estimation. So we want to figure out, you have a car, where exactly is it, or what is our belief over where it is? The issue with state estimation, as we talked about last time, is that you actually never observe the state. You only observe your own actions and measurements, right? And you have to get a belief over the state. So the XT is never known. And you instead only see U1 to T and Z1 to T, and you want to estimate a belief T of XT given Z1 to T, U1 to T, right? And so the problem of state estimation, the problem of posterior inference, is the problem of figuring out this belief distribution. And so the problem setting we're going to consider is that you have a stream of UZ, UZ, UZ. I think you'll ask the question of what happens if it's not polling every time. We're going to discard that case for now, but in general, we're going to assume there's UZ, UZ, UZ every time. And we want to get P of XT. And so the two important properties we're going to use are the Markov property on the state and the Markov property on the measurements, right? So the Markov property on the state says that if I knew xt minus 1 and ut, like you don't need to have any dependence on the past, right? And so this doesn't, just to be clear, this doesn't say that you know xt. It just says that if you knew xt minus 1, you don't need to worry about anything in the past, right? And so just a statement of conditional independence. Like xt minus 1 is still not known, but it's saying that if you did know it, it wouldn't depend on the past. So just saying that like the state, to be clear, the state is still hidden, but conditional on xt minus 1, xt is independent of xt minus 2. And so the past is independent of the future, conditioned on the present. And the measurement only depends on the current state. Again, current state is not known, but the measurement only depends on the current state. And so really a lot of this kind of like needs you to define what your state is carefully so that things are Markov. But once you have, like in many problems, it's quite easy to do. Once you have, like these assumptions are not that unreasonable. Right? And so if you're interested beyond the class syllabus, there's the easy way to like figure out this kind of conditional independence is when you have like this kind of a figure, it's called a Bayesian network or Bayes net. And a Bayes net like automatically encodes independences, right? So the Bayes net automatically says that like if you look at like this um intersection, right? Like it says that like this thing is independent of this thing, conditioned on this thing. And it says that this thing is independent of all the previous stuff conditioned on this thing, right? So we won't have enough time to get into this in class, but if you're interested after class, go look up an idea called deseparation. And deseparation kind of tells you how to take any Bayesian network and figure out which things are independent from which other things. So, but in our case, the things you need to care about is the Markov property on state and the Markov property on measurement. Okay, and the two objects we're gonna mess around with are the motion model, right? Or the dynamics model, the thing that tells you given xt minus 1 and ut, what is the likelihood of the future xt, and the measurement model, right? And so we'll try to cover, depending on how fast we go, we'll try to cover an example of a motion model. But the way you can kind of think about it is the motion model is like the physics of your car. It says that, okay, this is if your car was here, you applied this velocity and this steering angle, like where would your car be? That drawing is another car and some uncertainty. Um, and the measurement model is saying that, like, if imagine that you were in the world, right? This was your car, and this was like some set of obstacles, right? So let's say this was your car, there's some set of obstacles, and you have, like, let's say a laser rangefinder that goes in all directions. It is telling you what is the likelihood of getting a particular reading from that laser rangefinder. Okay? And so this really has to do with your sensors. This really has to do with the physics of your system. Yeah. Okay. Any questions so far? Does that make sense? We're with the premise. Good. Okay. So let's recap. We're gonna go through an example of Bayesian filtering with these pieces. And then we'll go into an example of a motion model for a car. Right? If you have that. So one of the challenges here is how do you tractably represent belief, right? And so if I think about this probability distribution P of xt given z1 to t, u1 to t, right? We talked about continuous distributions and discrete distributions and so on, right? The challenge is that you need a distribution to be expressive enough. So for instance, if you just had a Gaussian, the challenge is that if you like had uncertainty about whether the robot is here or here, a Gaussian is going to struggle to represent it, right? And so often you don't want to just stick with the Gaussian because the Gaussian will struggle to represent multimodal uncertainty. Right? But if you had, like, for instance, a discrete distribution, like let's say you had bins, let's say you had your like so you had a grid of where you could be, right? Imagine that you in a three-dimensional car, it's okay. But imagine you're the humanoid robot, 40 dimensions, you binned every dimension. Like imagine you had 100 bins per dimension, but 40 dimensions, you have 100 to the 40 bins. That becomes crazy. And so the challenging part in a lot of state estimation is how do you, and just probabilistic inference in general, is how do you represent a distribution that is complex enough while being computationally tractable? Like, for instance, Gaussians are great. They're like a super computationally tractable. They're all exponentials, but they can't represent like they can't represent things that are complicated. But discrete things can represent things that are complicated because it becomes computationally intractable super quickly. Right? So that's, in general, when you think about probabilistic inference, the balance is between expressivity and computational tractability. Right? And that's why these models like diffusion models and so on are so popular because they kind of let you balance those things nicely. Okay. We are going to specifically start with the abstract concept of the Bayes filter, and then for the next several classes after that, we'll instantiate a particular family of like how to represent P of xt, right? So for now, we're just going to let's just keep it as an abstract P of xt. We're going to try to represent P of xt in terms of other quantities, and then we'll like make it concrete after. All right. So the purpose of the derivation of Bayesian filtering is going to be to try and express our belief P of xt given u1 to t, z1 to t in terms of three quantities, the measurement, the dynamics model, and the previous belief. Right, so what we want to do is we want to express this kind of recursive update. So we want to express the belief at time t, terms of the belief at time t minus 1, and some combination of the dynamics model and the measurement model, right? And so our purpose is going to be to try and find the relationship between belief xt and some combination of your dynamics model. Oh, sorry, this is your measurement model, your dynamics model, and belief at xt minus 1. Right? So it's not going to be like closed form in case steps. It's just going to be recursive, so you keep applying it at every time step. Okay, so let's get into it. And so the key idea in the Bayes filter is to break it up into two steps, right? So we're gonna like start with our belief xt minus 1, right? And then we're gonna break it up into two steps, one where we incorporate a new action and one where we incorporate a new measurement, right? So if you look at the difference between time step t minus 1 and time step t, like what changes, you took an action and you got a measurement, right? And so we're going to break it up into two steps, one where you incorporate the action and then one where you take the measurement, right? So you can kind of think of it as like, I was at time step t minus 1, I took an action, then I took a measurement, right? And so we're going to start by incorporating the action and then we're going to incorporate the measurement. Okay, so the first thing we're going to do is we're going to say, okay, this is my belief of where I was. And given my action UT, this is going to be my belief of where I might be in the future, right? And so I'm going to introduce this, this notion of a belief bar, right? And so if you kind of think of the belief, like you have to be a little careful on the indexing here, okay? So if you look at belief at xt minus 1, it's the belief at xt minus 1 given evidence of actions from 1 to t minus 1 and measurements from 1 to t minus 1, right? It's going to t minus 1. And if you look at belief bar, you'll see that it's the belief over xt, not xt minus 1, incorporating one extra action, but no extra measurement, right? And so you like remember that you're getting the belief over the next time step, incorporating one extra action. So you can kind of think of this as ut and u1 to t minus 1. So it's the evidence from before with one extra action in there, right? And you have not taken a measurement yet. That makes sense? So we want to go from belief to belief bar. And the difference is we want to like figure out the belief over what the next time step is going to be when you take one new action. Yeah. Alrighty. So, and we want to do this in terms of our motion model, in terms of our dynamics model. Right? So we want to be able to express belief bar in terms of belief and our motion model. Yeah, does it make sense? So the main thing that gets confusing in the Bayesian filter is just the indexing. So just be careful about the indexing. Okay, so intuitively, like how do we think that belief at t minus 1 and belief bar are going to be connected? Any guesses? So maybe one way of intuiting this is, right, you can think of belief at time step t minus 1 as saying like, oh, if there's like these 5 possible positions I could be in, right? The question is, and then say I have like 0.2, 0.1, 0.3, 0.2, I'm not sure yet, and 0.2, right? That's my likelihood of all the 5 positions before. I'm gonna like take some action. Let's say like ut is equal to something. Like, let's say move this way, right? Now the question is, how does the probability distribution over states change, right? And so one way I find it useful to think about this intuitively is that you like from you take like every position that you could have been in at t minus 1 and then transition to the next time step with your motion model, right? So you say that like, imagine that I was perfectly at xt minus 1, at this particular xt minus 1, then like what is the likelihood of my future xt, right? And so this gives me some likelihood over future things. And then if I was at this one, what is the future likelihood that I would be in these different states? If I was in this one, what is the future likelihood that I would be in these different states? And then I sum them up, right? So it's kind of like, it's like, see if I can erase this. Like if I could be in these 5 positions, right, in order to get the belief at the next time step intuitively, you can say that the likelihood that I'm going to be here in the future is equal to like the contribution from, and let's say like this thing is a little hard to see, but let's say my belief was somewhere in here, right? Like the belief at this time step is going to be the belief at this time step multiplied by the likelihood that I transition to here, plus the belief at this time step times the likelihood that I transition to here, plus the belief at this time step, plus the likelihood that I transition to here, right? These are all the places that I could have been in. And I look at where the motion model takes me and I sum those up. Right? So intuitively, you can kind of think of it as like you're pushing forward through the motion model and then you're integrating integrating over it, right? So it becomes a little easier when we work out the math, but that's kind of the intuition. Okay, so let's consider something discrete for now, right? But the answer, which will work to, right, is that belief bar xt is equal to a sum over xt minus 1. So this is not indexed. Sum over xt minus 1 of p of xt given ut xt minus 1 times belief at xt minus 1. Right, so it's kind of saying like for every single xt minus 1 in the world, this is your belief that you were there. And this is the likelihood that you transition from xt minus 1 to xt. Right, so it's useful to think of it like a graph almost. So you're saying that like, this is the likelihood that my car was here. And this is the likelihood that if I was in xt minus 1, I would have transitioned to xt, right? And so the solution is going to be basically a sum over xt minus 1 of the motion model times the belief at xt minus 1. Right? So that's how I'm going to go from belief at xt minus 1 to belief bar at xt. Okay, so we are going to try and work this out and derive this, right? So the important things we're going to need to derive this is we need to start by defining belief and belief bar, right? And so your belief, if you remember, is p of xt, or your belief bar is p of xt given u1 to t, z1 to t minus 1, right? So it's saying that like, this is the likelihood at xt when you incorporated the new action, but not the new measurement, right? And your belief at xt minus 1 was p of xt minus 1 given u1 to t minus 1, z1 to t minus 1. Okay, we're going to try and connect these. So you guys are going to help me work it out. I'm not going to monologue. Right? So if I want to connect these, right, let's remember some axioms of probability, right? Like the first one is that if I ever want p of x, I can write it as a sum over y of p of x, y. And then the second is the Markov property, right? Like the only two things we're going to use is this thing, which we're going to call marginalization, right? Marginalization and the Markov property. And so we're going to derive it with these two things. Alrighty, so help me work it out. Now I have belief bar on the left-hand side. I want to express it in terms of the right-hand side. How might I start doing this? And so just a hint is you want to use this property. P of x is equal to sum over y of P of xy. Ideas? I know it's early in the morning, but we're going to be thinking. You want to express, I want to somehow get, it's useful to maybe add in the indexing variable here. This is xt minus 1, right? I want to somehow get like this sum in there, right? Like I know the right-hand side is a sum. I want to get a sum. Yeah. That's right. That's right. So what you're going to do is you're going to introduce xt minus 1 as a variable and marginalize it out, right? So you can say that if I know that p of x is equal to sum over y of p of x comma y, right? So in this case, I'm going to say x is equal to xt minus 1 and y is equal to x, x is equal to xt and y is equal to xt minus 1, right? So I'm going to introduce an additional variable xt minus 1 and sum out over it. Right? And so the way that's going to look is I'm going to use this property and I'm going to introduce an additional variable xt minus 1 and sum out over it. Right? And so all this is saying is like almost ignore all the stuff to the right side of the bar for now. Like it's just a conditioning. It doesn't matter, right? So like the stuff on the right side of the bar remains exactly the same, right? But in some sense, what I'm saying is that P of xt is equal to a sum over xt minus 1 of P of xt, comma, xt minus 1, right? Which is exactly the same as this. So I'm just saying if I have a joint distribution and I sum out over one of the variables, it just gives me the marginal distribution. And so what I'm going to do is I'm going to introduce another variable xt minus 1 and sum out over it. Yeah? Does it make sense? Ask questions if it doesn't. Don't look lost. Yeah.
You should use the variable like that. Doesn't change the probability?
No, because you're summing out over it. So like the important thing is like if you look at P of x, you can say that P of x is equal to sum over y of P of x comma y. So like what I've done here is I've introduced xt minus 1. I've taken the joint distribution and then I've summed out over the extra variable that I introduced. Right? And so it's kind of like, it's the same as if I have like P of a comma b and I sum out over b, I'm just at play. Right? So it's kind of like, if you like, it's a little more confusing to go from left to right. But if you go from right to left, you have this joint distribution and then you just sum out over xt minus 1. And then you just get it. Here's another easy way to think about it, which is that if you have sum over y, P of x comma y, use the definition of the joint distribution. So you can write the joint distribution as P of x times P of y given x, right? And then P of x doesn't depend on y, so you can take it out, right? And so then you get P of x times sum over y of P of y given x, right? But P of y given x is a probability distribution, so its sum is 1, and so you just get P of x.
Okay.
Right. Okay. Does it make sense? So the important thing is we introduced this additional variable xt minus 1. We summed out over xt minus 1. And those are like the left and the right-hand side are exactly the same. We just use this identity. Okay. Now, what's the next step? Yeah. Sorry. That's right. Okay, so you try to split like sorry. You try to think of let's abstractly think of this as like P of A comma B given C, right? Where this thing is A, this thing is B, this whole thing is C, right? You want to kind of like split them up into some version of P of A given C times P of or say some version of P of A given B comma C times P of B given C, right? And so if you ever have it's kind of the same rule as is when you have a joint, right? If you have P of x comma y, you can write it as P of x given y times P of y, right? You want to express the joint as a product of the conditional and the marginal. You're going to do kind of the same thing here, right? Okay, so again, you're going to use the property. P of A comma B given C is P of A given BC times P of B given C, right? This is the same thing we did last class. There's no magic here. And so we're going to split it up again, right? And so we're going to split it up. We're going to separate the xt and xt minus 1 terms, okay? So I think the thing that gets a little confusing here is like too many indexing variables, like confusing. Like I would say just like forget about the indexing variables for a hot second, right? Just think about the xt and xt minus 1 and separate them, right? And so you want to write this as almost like let's call the indexing variable c for a second, right? Or like the history as c for a second. You want to write this as p of xt given xt minus 1 and c times p of xt minus 1 given c, right? So you want to separate those two variables. Okay, so what we're going to do is we can write this as p of xt given xt minus 1 and u wanted t, z wanted t minus 1, times p of xt minus 1, given the same history. And so you've just like taken this joint distribution of xt comma xt minus 1, separated out into an xt given xt minus 1 and an xt minus 1 distribution. You just separate out the joint into the conditional and the margin. Okay, and then how do we convert this thinking back into the form that we care about? One more step. The Markov property, right? You just say that like if you look at this guy, it's saying xt only depends on xt minus 1 and ut and does not depend on anything else in the past, right? And so the last line is just the Markov property, right? And so the last line is the Markov property, and then you'll note that this thing is basically belief at xt minus 1. This is your dynamics model, and then you directly get your connection, right? Okay, so I'm seeing lots of people looking super lost, but I am not a mind reader. So let's go over it again and ask me questions, right? So the important part is we have belief at xt minus 1. We want to get to belief bar, right? And our update is going to look like take belief at every single xt minus 1 and multiply it by the likelihood that you went from xt minus 1 to xt when you took the action ut. And then you sum it up over all the xt minus 1s. Right? So it's kind of like, imagine that I'm like trying to figure out what is the likelihood that I'm going to be here. I'm going to say like, let me take the contribution from all the xt minus 1s that I could have been at, weighted by how likely I was in each of those xt minus 1s. Right? So like each possible state in the past has some likelihood of getting here. I like weight that by how likely I was in each of those states in the past. And the way you express that mathematically is you're going to say that the belief bar is equal to the sum over xt minus 1 of p of xt given ut xt minus 1 times belief at xt minus 1.
But the UT supposed to be like a distribution of where it could be, or is UT supposed to be like this is the intended action, and assuming that it was going to be.
Ut is not a distribution. Ut is like a known action. It's like I was at xt, I don't know xt minus 1. I have some belief over xt minus 1, and I know that I took this action. So ut is a deterministic entity, or like near deterministic, right? But you're gonna like, essentially you can kind of think of this as like, there's like a table, and ut tells you like which entry of the table you're taking to move forward.
X one is like a carbon beat freedom spot.
Yeah.
And UT is like I drive the car forward one day.
Exactly.
And XT is like it's forward 1/3 of all day.
Exactly. Plus, like the reason it's not just trivially that is because there's some noise.
Yeah. I just want to clarify the definition of UT. So given now I'm like a XT, is UT the previous action that makes me to be XT? Or
Yes.
UT
Yeah.
is the future?
Yeah. That's a good question. UT is the action that you took from xt minus 1 to get to xt. So UT is the previous action. It's a little confusing with the indexing is just a choice. So like you were just asking, basically, belief of xt minus 1 is if there's like 3 different positions the car could be in. UT is saying, I drove forward. And then belief bar at xt is saying before I take a measurement, like it's like before I took the action, I thought my car was here, right? And then I took an action of moving down one step, right? And after I took the action of moving down one step, I have some likelihood it's here and then some likelihood it's here because I'm not exactly sure the actions do like just move one step, right? There's some uncertainty. And so we'll go through some examples of what this looks like in a second. But that's the basic concept. Yeah. It does. So you just apply this recursively. Right. So this is connecting belief bar of xt to belief of xt minus 1. And then belief of xt minus 1 will be expressed in terms of belief of xt minus 2. And so it's like you apply this at every single step. And so you start from belief at x0, and then you take an action, and you apply this update to get belief bar at x1. And then you take a measurement, then you go from belief bar to belief at x1, and then you repeat them. So it's kind of like as your robot is running, you run like this update, which is the dynamics update, then you run the measurement update, which will go over next, and then you do the other.
Is the second term product at the bottom, like probability x t minus one, given all the previous actions measurables, is that kind of like if we were implementing this, would we kind of keep that probability as a running?
It's a running, exactly. So it's kind of like your belief is your running estimate, and then you keep updating your running estimate, right? And so you like the measurement rule and the dynamics rule will be the same at every, like it's the same form at every time, but your like value change. Yeah, so good. Okay, let's go over. Yeah, go ahead.
So is the reason we solve for that equation so that we can use it recursively?
Yes, exactly.
But then if we solve to use it recursively, then the second term kind of like being like a rolling thing, then doesn't that kind of the purpose of having like a recursive thing, just apply once?
So it's not backwards recursive, it's like forward recursive. So it's kind of like I like the way this will kind of work is that I like start with belief at x0. Let's say some defined thing, right? Like I just have some guess of where I might be. Then I take an action u0, and then I get to like belief bar of x1 using this thing. And then I take a measurement z1 or whatever, and then I go to belief at x1. And then I repeat it again. So it's kind of like every time I take an action, I perform this update, given my current estimate of belief. Right? So it's kind of like I started with some belief, right? I started with some belief in the world. All this thing tells me that is like you can kind of think of belief xt minus 1 as my current belief. And belief bar xt is my future. It's predicted. Yeah, it's predicted. And so it's like that's what I know right now. I took an action. How should I do it? And so it's just like tell me how to perform. Okay, any more questions? This is a little bit confusing, so it's fine to just like, be slow here. So in general, like you can kind of think of this as like it's often called like a push forward update. You're pushing forward. You're saying that like essentially I'm gonna weight xt minus 1 by their likelihood in my current belief, and then I'm gonna push them forward according to the dynamics, right? And so in some ways it's like the reason you go from like a really narrow thing to a wider distribution here is because of the uncertainty in my motion model. It's like this is my belief before, and then the motion model had some uncertainty. So it said that I didn't land up here perfectly. I would have some uncertainty, and so then I broaden it. And so over time, unless I do the measurement update, the uncertainty will keep growing. Right. So you can kind of think of it intuitively as like the motion model adds uncertainty, and the measurement model reduces uncertainty. And so it's like I moved, my wheels have slippage and there's some uncertainty, so I don't know exactly where I am, and so I remeasure, and then I reduce uncertainty. So I increase uncertainty, reduce uncertainty, increase and reduce, increase and reduce. Okay, so let's go through the dynamics update, and we'll put things together, go through some examples. Right, so we've gone from belief to belief bar, right? Now I need to go from belief bar at xt to belief at xt, right? So belief bar, remember, is when I incorporate a new action, but not a new measurement, right? And now I want to incorporate the latest measurement. So I've incorporated the latest action, not the latest measurement, right? So belief at xt is going to be, again, if you focus on the indexing, it's incorporating the latest action and the latest measurement. Okay? And so the only difference between belief bar and belief is that you've added one extra measurement on the right. Okay. So we want to express this using the measurement model. So let's say we had a measurement model of P of zt given xt. We want to express belief bar in terms of belief using the measurement model. Right? Okay. And so again, intuitively, it's useful to think of it this way. It's like if let's say I did my motion model. My motion model said, okay, your car was here. I took a step. Now I think my car is in one of these K positions. I have some uncertainty, right? And then I like took a measurement, right? I took a measurement. I shot some laser beams. The laser beams gave me some readings, and the readings were like some level of some set of distances for each of these like laser beams that I shot out, right? And so you can kind of think of the measurement model as saying that like, well, given the readings that you got, it's super unlikely that you were in any of these positions, right? And so if it's super unlikely that you're in any of these positions, you can refine your belief to just be those two positions. And so you're saying that like my motion model went from there to like more uncertainty. But then my measurement says that like, given what I saw from my measurement, it's pretty unlikely that like any of these things are really where I am. And so I like you can almost think of it as like eliminating those positions, right? And it's like a softer version of that, but you're saying that my motion model is kind of or my measurement model is kind of inconsistent with these three positions. So I eliminate that and I refine my belief to the things that it could be, right? And so like, for instance, if I like got a reading that there's a wall in front of me, it's unlikely that my car is like facing this way, right? And so you like eliminate that out. Okay. So that's the intuition behind the measurement model. The motion model says like, this is where I should have moved plus some noise. And the measurement model says, these are the things that are unlikely given your current measurements. Let me refine my belief. And given your current belief, you act, you refine, you act, you refine, you act, you refine, you act, you refine. That's it. Okay, so let's work through what this looks like. Right, so we want to express belief in terms of belief bar, right? And the answer is going to look like this, and we're going to work out how to get there. Right, so the answer is going to say that my belief is equal to, let's say some normal, the normalizing term gets a little confusing, so let's just call it eta for a second, right? It's going to be some normalizing terms times P of ZT given XT times belief bar at XT. Right? So it's going to say like, let me take my belief bar and let me weight it by the likelihood that that measurement was produced by that state. Right, so it's kind of like, imagine that you had a table of like belief bars at XT, right? And then you wanted to get to your table of beliefs at XT. Right? What you're going to do is you're going to take, sorry, you're going to take each of these values. You're going to take each of these values. You're going to multiply it by P of ZT given XT for that particular XT, right? And you're going to like re-weight the distribution that way. So for instance, if it's super unlikely, like that P of ZT given XT is going to be close to 0. And if it's very likely that P of ZT given XT is going to be high, it's going to be 1, right? And so the things that are likely will be weighted high, and the things that are unlikely are going to be zeroed out. And the only reason you need the normalizing constant is so that it becomes a probability distribution again, right? And so you can kind of this intuitively really makes sense because it says that like belief bar was where you thought you were. You multiplied by like P of ZT given XT because that's how like likely you were to get those measurements, and you renormalize. Yeah. Intuition kind of parses here. You're in with me? Okay. So we'll go over an example with numbers. It'll make it a little easier. But the way we're going to derive it again is honestly just using the base rule. That's it. And so we're going to try and write out what belief is and try and collect it to belief bar. So belief at XT is probability of XT given U1 to T, Z1 to T, right? And so it's important to like open up the indexing a little bit here. So you want to express Z1 to T as Z1 to T minus 1 and ZT, because that's the one you care about that's the latest one you care about. Right. So this is just saying that like Z1 to T is just an array of Z1 to ZT minus 1 and like the latest one, ZT. So let's just like separate them for the sake of simplicity. Right. And then we're just going to try and use Bayes' rule. Right. So if you remember how Bayes' rule worked, right? Bayes' rule says, this is the version of Bayes' rule with conditioning, right? So if you remember what Bayes' rule said, it said P of y given x is equal to P of, oops, I think you guys used the other one. P of x given y is P of y given x times P of x by P of y, right? You're just going to add a conditioning variable z to everything, right? Doesn't change base rule. You just add conditioning to every single entity here. So this is the version of Bayes' rule we're going to write. P of y given xz is P of x given yz times P of y given z divided by the sum of them, right? And so the important mapping we're going to make here is that y is going to be xt, x is going to be zt, and z is going to be the rest of the conditioning, right? And so we're literally just going to apply Bayes' rule. We're just going to set in the Bayes' rule instantiation we have, we're going to set y is equal to xt, x is equal to zt, and z is equal to u1 to t, z1 to t minus 1. And like the intuition of how you, like why you want to do that is because you really care about expressing like this is the history that you had until belief bar, and so you just want to like keep that as conditioning, but you want to like express x given z in terms of z given x because that's your measurement model, right? And so we're just going to try and we're going to take this belief and we're going to try and stick the measurement model into it by using the Bayes rule, right? So so we're just literally going to apply the Bayes rule, right? So the Bayes rule is going to say, let's try to unpack each term one at a time. So this is P of x given y comma z. Let's say if you remember, y is equal to xt, x is equal to zt, and z is equal to like u1 to t, z1 to t minus 1. And so the first term is going to be P of x given yz. So it's going to be P of zt given xt and u1 to t, z1 to t minus 1, right? Just literally mapping all the terms, right? Now, if I have this term, how can I simplify it? Markov, exactly, right? And so the Markov, like this stuff goes away. Beautiful. And so the first term we're going to get is like this guy is going to simplify down to P of zt given xt, which is nice, right? And then what's the second term we get, right? The second term is just P of y given z. Again, y is equal to xt in our case, and z is equal to u1 to t, z1 to t minus 1, right? And so P of y given z is just P of xt given u1 to t, z1 to t minus 1. Have we seen this before? Just belief bar, right? And so now we're golden because like the numerator is just P of zt given xt with the Markov property. And then the second term is just belief bar, right? And so all we get is the numerator is P of zt given xt times belief bar, and the denominator is just a sum of that over all the possible positions so that it's a valid probability distribution. And so I'm hand waving over the sum right now, but it's more of a pain in continuous values because you have an integral. But if it's in a discrete thing, it's just the sum over all the positions, right? But intuitively, it's just saying take your previous belief multiplied by P of zt given xt and renormalize. That's it. Okay, so to kind of put the pieces back together, you're gonna like have this running update that you keep doing. How are we doing with time? Oh, well. You have this running update that you're going to keep doing. You're going to start from belief at x0. You're going to take an action. You're going to run it through your motion model. Right? The motion model is going to say, okay, like this is where I think you're going to go given your current belief. Then you're going to take a measurement. You're going to reweight all the beliefs by your measurement. You're going to renormalize. You'll take another action. You'll run it through the motion model again, and you'll repeat. Right? And so like the cadence of this is going to be first time step, take an action, go from belief to belief bar, take a measurement, go from belief bar to belief, repeat, go from belief to belief bar at the next step. Right? Okay. And so it's the reason you wanted it to be like the reason it's a Bayes filter is because we use the Bayes rule here. And the reason it's a filter is because you want it to be like this recursive update where you just keep it running. So you don't have to keep track of a huge amount of memory. Like Isaac was saying earlier, it's basically you just keep track of your running belief and belief power. Like you don't have to keep track of anything that's in the past. Like you just need to keep track of your current belief. Right? And so you just like your data structure that you need to store for your belief is just like a table of like states, not states times history. So the same tool is useful across lots and lots and lots of things. So localization, mapping, simultaneous localization and mapping, solving form DPs, machine learning, they're like the same tool. HMMs, a lot of them use the same tools, but all of them are basically the Bayesian filter. The Bayesian filter, motion model, and measurement model. That's it.
So your normalization factor is taken over like all XP, right? Which is like every single state.
Yeah.
But is this like what you're mentioning about it being computationally intractable? That seems like very.
Yeah, it's kind of, yes. So we're gonna do a few different things. If it's discrete, it's just like sum over a table. It's not that bad. If it's continuous, then it becomes a huge pain. And like the bulk of probabilistic inference, the whole field of generative modeling is just trying to deal with that freaking denominator. And so there's lots of different ways to do it. The one that we're going to do in this class is we're going to represent everything with a Gaussian. If you represent everything with a linear Gaussian, then there's a closed form solution to it. And so you don't have to fight the integral. If it's not a Gaussian, and I guess the second way we're going to do it is by representing things with particles. And then you just like normalize over the particles. So it's almost discrete. But we're not going to fight integrals. But it's a good question. Okay. I think the example will take a little more time. So let's go through that next time. Any more questions before we wrap up? Yeah.
That doesn't. The belief one fully rely on.
Oh yeah, you can be flexible with it, right? Like if you didn't have if you didn't want to do the action step, you could just skip it. Now, should I skip it? Probably no. I mean, it'll still work because you'll like update your thing with your latest measurements, but it's kind of like throwing away information you don't. Yeah.
I mean, are there instances where you would not skip a step?
If your actions are super noisy. If your actions are super noisy, or you're like, I need more certainty before I act. So it's like, okay, before I act, I'm just going to take a ton of measurements. I'm going to refine my belief as much as I can, and then I will take it. So I wouldn't be like, the cadence I mentioned is like the usual one, but it doesn't have to be like 1:1. You just like, anytime you get an action, you take the motion step, and anytime you want to refine to the measurement, you take the measurement step. But I could take like 10 measurement steps at once before taking. Good question. Okay, let's wrap up for today. I'll see you on Wednesday. Thanks. Yeah.
I want to clarify like how exactly the split works in terms of like UT to like UT, like the split in the time step. Yeah.
So that's we have P of X P because we want to be equals P minus 1. First thing we did, we added XP minus 1. Give X P minus 1. So we want to be C1 to P minus 1. This is part of this. And then here we're going to split this up into P of XP given XP minus 1. Q1 to P, V1 to P minus 1. Times P of XP minus 1 given U1 to P minus 1, V1 to P.
I guess. Okay, well, I guess like intuitively this makes sense that we have to split it into U to like 1 to T minus 1 because you can't really have 1 to T if you have only state like T minus 1.
Yeah.
But like, can we do that? Can we just split it such that it's like T minus 1 where
So actually the way you properly split this, I skipped over hand waved over a step, is basically you actually like with let's say you keep this conditioning and call it C, right? And then let's write this as P of xt given xt minus one C times P of xt minus one given C,
Mhm.
where C goes from one.
Oh.
And so, okay, so then let's look at each step one at a time. So this is P of xt given xt minus one, u1 to t, z1 to t minus one. By the Markov property, everything else goes away except for ut. Right? So the first term will simplify to P of xt given xt minus one, ut.
But isn't that can only go up to t minus one because that's no future step.
So if you're thinking about a probability distribution, it could
Yeah.
depend on the.
Yeah.
But I think so. Let me explain where that actually goes away from. But basically, the first step just becomes your dynamics model.
Right.
The second step is the one where you really astutely noted a thing. But basically, it's saying that like if I have P of xt minus one, it's u1 to t given z1 to t minus one. And I like magically disappear.
Yeah, I was like, I guess that makes sense, but at the same time, I'm like, I don't know.
Yeah, magically disappeared one, right? So here's how you can explain it, right? It's like if you like the assumption in Bayesian filtering is that the thing that is taking actions doesn't magically have more information about the state. So the thing that's taking actions is like an exogenous process taking action. So it doesn't have magical extra information about the state.
Right.
So everything that is used to choose UT is like all the information that's already in U1 to T minus one, Z1 to T minus one. So like I was at XT minus one, right? And to get here, I don't know XT minus one. But to get here, I took U1 to T minus one, Z1 to T minus one. And then I'm going to take some action UT, right? But the way that I'm going to take this action UT is using only this information, right? And so like this doesn't give me any extra information besides what's already in here.
Okay.
And so basically you can like essentially this is the assumption in Bayesian filtering is that if UT has some magical information about XT, that's different. But like if UT doesn't, then UT doesn't give me any more information about XT minus one than I already had from UT minus one, Z1 to T minus one.
So it's not inherently that it disappears, but we just kind of ignore it because it's not like
we ignore it because it's conditionally independent.
Yeah.
Right? And so you can say that it's like U1 to T minus one, Z1 to T minus one, and UT, but like
The UT
like
goes away.
this and this are conditionally independent given this.
Yes.
And so I think this one.
Okay.
Good. I'm really. I was hoping no one would catch it.
was just bored.
No, it's a good finding. It's just a little complicated to explain in class, but it's a good point.
Just want to clarify about this because I just get confused about the